Welcome, everyone. Fei Qi will be speaking on extensions of modules for a meromorphic open string vertex algebra.
Okay,
yeah, start when
thank you for the invitation. And it's been a while since I spoke in this seminar, and now I should report the work I have done last year. Currently, the paper is actually on archive for almost a year, and there are still some minor mistakes in that paper. So, but let me actually use this opportunity to clear something up. Okay, so the main topic of what I want to talk about is its extension of modules. And just as you all know, vertex algebras are can be considered as analogs of associative algebras, or in particular commutative associative algebras. So let's first revisit the notions in an associative algebra. So basically, I will just start with the extension and cohomology for associative algebra case. Then I will tell something about what is a meromorphic open string vertex algebra and what is their cohomology theory. And then I will discuss the extensions and cohomology in the Mossbach case. And then finally, at the last slide, I will just propose a program of computing the extensions explicitly. So this computation program was not realized until very recently. So it's not in the paper yet, but in the next revision, I will just submit it. Okay, so let's start by the extension of left modules for an associative algebra. So the setting is, so first let A be an associative algebra, and I think I want to emphasize that this associative algebra, we will just consider an associative algebra over the complex numbers. And let M1 and M2 be two left A modules. Then, so then if U is a left A module that fits in the exact sequence 0 to M2 to U to M1 to 0, so in this case, we will call U an extension of M1 by M2. So notice, obviously, 1 and 2 is actually located in a weird way. I don't know why, actually, this has been a convention in the area. Anyway, okay. So any U fitting in this exact sequence is called an extension. And then two extensions are equivalent if there exists a homomorphism from U1 to U2 such that this diagram commutes. And notice that in this diagram, so we are requiring the maps connecting M2 and M1. We are requiring these maps to be exactly the identity maps, and we are not allowing any other automorphisms of M1 and M2 appearing over here. Everything. So the equivalence relation is defined using identity maps in these locations. Okay. So then the ext1 group of M1, M2 is simply going to be the set of equivalence classes of extensions of M1 by M2. So this, I guess this is the notion you have all seen in undergraduate homological algebra class. And then, let me actually discuss a little bit about the coaxial cohomology. So let A be an associative algebra over the complex numbers, and let B, so over here we will like B to be a bimodule. So then we will use the set of linear maps, C-linear maps from A tensor N to B as the cochain, as the space we use for the cochain complexes. And then for two cochain complexes, we will define a coboundary operator connecting two cochain complexes of order n and n plus 1. So given a map accepting n inputs and with the image in B, we will define delta n of f to be a map accepting n plus 1 inputs. And this is, I will just list them as A0 through AN. So there are n plus 1 elements inside here. And then, I would define delta n of f to be a map sending these n plus 1 elements to the following guide. So the first element is you pull the A0 out, and then you let the A0 act on the image of A1 through AN from the left. So the image of this guy is an element inside the B, and remember B is a bimodule, so there is an action from the left. So I will just let A0 act on it from the left. So this will result in an element inside the module B. Then starting from the second spot, I will be just asking, I would be getting at so for the next spot over here, so I will be contract A0 and A1, because A is an associative algebra, A0 times A1 ends up as an element inside the algebra. And that way, together with A2 all the way up to AN, I have got n elements over here. I will just consider the image of this tensor. So where the first dot plot is obtained by contracting the first and the second location over here. Okay, so this is just and then moreover, I wanted this. I want to have got an alternating sign in the front. So generally speaking, so I can do this for every spot over here, and obviously here I have got it should be I-1 over here. So contracting at the ith spot, so then and then together with all the n-1 elements, so I will also get an element, get an n tensor, and then the image. I will just consider the image over here, place it with the sign, and then I'll add it into the sum over here. All right, so these are the intermediate terms obtained by contraction. So these guys actually are obtained all by contractions. And finally, the last term is basically the image of f restricted to the first n guys over here. So what we get is going to be an element inside, but the bimodule, and I will let the am to act on this bimodule elements from the bimodule from the right. All right, so then I will just say that this is the image of an f in the n plus first order, the n plus first degree of the n plus first quotient complex over here. Okay, so this is the co-boundary operator, and as a result, yeah, this is actually follows from a very classical result in the 60s. That this I think it's much earlier. I think it's actually in the 20s, maybe. So that the following sequence is actually going to be forming a quotient complex delta squared. So the composition of 2 delta equals to 0, and then we could define the nth Hochschild cohomology to be the quotient space of the kernel by image. All right, so this is how the Hochschild cohomology is defined in general. Okay, so one of the most important things we want to keep in mind is what's going on, what's its connection with the ext1 group. And here is the situation. So we will just construct a very special bimodule. And this bimodule is simply going to be this built upon the space of linear maps from M1 to M2. And then, so where M1 and M2 be two of the left bimodules. And then I can make this space and a bimodule using the following actions, and the actions are defined in the most obvious way. So I will let A act on F from the left by simply sending M1 to a left action on F of M1. So this is a left action of an algebraic element A on F. Okay, for the right action over here, so I would just let A act on the in the codomain. So basically speaking, so the left action is the action on the codomain, and the right action is the action on the domain over here. So you can track that these two actions makes the space of linear maps between from M1 to M2 and a bimodule over here. All right, so then this is the big theorem over here in the so then we could see that the equivalence classes of extensions M1 by M2, so namely the ext1 group, are described by the Hochschild cohomology, namely the first cohomology with respect to this bimodule over here. And this applies similarly to the higher degree ext groups as well. So extm is also described by the nth Hochschild cohomology associated with this bimodule over here. Okay, so this is the story in the classical associative algebra. All right, so our goal is to get a generalization to vertex algebras and also meromorphic open strings vertex algebras. And as you expect, well, the main difficulties of all such kind of generalizations lies on the convergence. All right, so I would like to go over at the very least the axioms on meromorphic open string vertex algebras, because this algebra, such kind of structures are very weak. So we will. Yeah, it's not so demanding as a vertex algebra. So then,
Fei, I have a question. Can you go back?
Yes, please.
Why is it important that it's a bimodule, this home?
For
the Hochschild cohomology? Are you using that?
Because Hochschild cohomologies are defined over a bimodule. You need to have got, in order to get the co-boundary operator, you see the first term you need to
I
have
got
the
you.
left
Okay,
action.
thank you.
The
Thank
right,
you. Yes.
the last term you need to have a right action. So it's
Thank you.
necessary for us to start with a right a bimodule. Yeah.
Thank you.
Yeah. Yeah, of course. I mean, if you were a commutative associative algebra, then you could also define well, a trivial bimodule actually. So a module for a commutative algebra is trivially a bimodule using the trivial right action. So that's very obvious. Yeah.
Thank you.
Okay. Now let's actually go over the axioms of meromorphic open string vertex algebra, and I will just use abbreviation MOSFA, so it will be much shorter. So we require a Z-graded vector space, and this is graded, and the grade we also will call the grading to be given by the weights, and then we will require a vertex operator map, so sending u tensor v to y of uxv, and we will require a vacuum element 1 over here. But on the other hand, we do not require any conformal elements, so that's one important difference. All right, so the axioms are all quite simple. So first, we need to have got the axiom for grading. So the grading has to be lower bounded. So this means when n is sufficiently negative, so the nth graded vector space, it has to be 0. So this is so we require the grading to be lower bounded. And we require the D bracket formula. So basically means, well, here the both face D over here, this basically plays the same role as the L0 operator, but except that you do not need a conformal element to define the L0. We can simply define the capital D. We can simply define the lower both face D by the grading. We will have a grading. We just let D to be the grading operator. Then we require these commutator formula to hold regarding the grading D operator D and the irregular vertex operator. So this is basically the same as saying that if given a vertex operator y of v of x, and then if v is homogeneous and moreover its component is going to be vn over here, then this bracket formula simply means weight of vn. So this is supposed to be weight of v minus n minus 1. So this is, yeah, basically speaking, that's the requirement. That's basically the equivalence formulation of this lower D bracket formula over here, right? So yeah. Okay, so these are the axioms for the grading. You can think of it as we need an L0 element, but we need an L0 operator, but we don't necessarily, that is not necessarily coming from the conformal element. So yeah, it simply comes from the grading. All right, and also as regular vertex algebras, we require the axiom for the vacuum. So we require the vacuum, the vertex operator associated to the vacuum acts as the identity. And we also require the creation of property. So namely, any vertex operator acts on the vacuum is going to be giving out the formal power series with no negative powers. And moreover, the constant term has to be the same as the element u over here. So that's these are all standard with the definition. All right. Aside from these axioms, we also need to have got a capital D operator, and we require the capital D operator to be satisfying the derivative properties and D bracket properties. So here, again, the capital D is kind of playing the role as L-1, except, again, we do not really need a conformal element to define this capital D operator. We could simply define the capital D as using the formula. So this is basically means you take the derivative of the vertex operator action on the vacuum, then you take the constant term. So in other words, so if you expand this power series out, the first one is certainly going to be u, and the next term will be du times x. And we will just pick the coefficient of x as the definition. We will just use that as the definition of du for this capital D operator. Then we will require that first the derivative of vertex operators is captured by these capital D operator, namely, y of dv applied to the vertex operator associated with the dv is going to be giving out the derivative. And moreover, the capital D will also satisfy the commutator formula. So the commutator is also going to give us the derivative over here. Okay, so you see that over here, so L-1 is now also have got a very natural definition. So we do not need a conformal element for this to handle the situation over here. Okay, so these are the.
I'd like to ask a question. The bottom line, is that a consequence or is that a requirement?
Can you repeat the question again, actually?
Is the bottom line
Bottom
that's
line over
a
here.
consequence or that's a requirement?
This is a requirement, so this is an axiom.
Okay.
Yes.
Okay, thank you.
Yes. Okay. Yeah, so these are the side axioms over here. And of course, the most important axiom for the meromorphic open string vertex algebra is the so-called weak associativity. So over here, we require that for three elements inside the vertex operator, inside the vertex algebra, so we require the existence of a number p, and the number p has to depend only on the first and the last, so namely u1 and v over here. And then we require the weak associativity hold, so x0 plus x2 to the so these the products and the iterates are the same after the multiplication by a sufficiently large power of x0 plus x2. And moreover, it's important to notice that this power has to be depending only on u1 and v, and it could not depend on u2. So this is a necessary condition to make sense of the products and iterates of any numbers of vertex operators. So if we do not have this dependence, if with the p over here can possibly depend on u2, then we will have to modify the definition to a stronger form to make sure that the products and iterates all converge. Okay, so as you all know, in a vertex algebra to the usual sense, aside from the weak associativity, we also have the weak commutativity. But in the current situation for meromorphic open string vertex algebras, it's just like an algebra of vertex operators where only weak associativity holds and weak commutativity is not required to hold. Okay, so to some sense, if you view vertex algebras as, if you view a vertex algebra as an analog of a commutative associative algebra, then MOSVA is simply the analog of associative algebra that is not necessarily commutative. Right, so these are all the axioms. Now, a few more. So once the algebra is clear, then we could actually define the left modules and right modules using the philosophy that all the defining property of an algebra that makes sense should hold. So this has been a very widespread philosophy in defining the modules and also the related notions. So left modules is just defined in the similar property, and the right modules, for the right modules, on the other hand, we will need to actually change a little bit. So we would like to actually make the properties of intertwining operators of the types WV/W. So namely, we will just be defining something like y of wx of v. So this is actually supposed to be an intertwining operator sending w tensor v to w. So then we will use the philosophy that all the defining properties of such intertwining operators should hold for the for the axiom. I'm sorry, I have to remove this. Actually, this is not a part of supposed to be. I want to actually discuss in detail. Okay, finally, the bimodules is just defined as a space. So the space has a left module and the right module structure, and moreover, we require them to be compatible to each other. So remember in the associative algebra, bimodule, the compatibility of the bimodule is simply expressed as in associativity. So given the element in the bimodule, you first act on the element from the left, and then you act on the element from the right. So the result should be the same as you first act an element from the right, then act on the element from the left. So this compatibility is basically like an associative. It basically looks like an associative relation among the left vertex operator and the right vertex operator. So yeah, everything has been written down in my previous paper on JMP actually. So okay, all right. On the other hand, I should really give a remark, and this remark did not arise when I was first drafting the paper over here. So there has been a very recent discussion. I think the discussion happened in August, just last month. There has been a discussion regarding whether or not we should have a capital D operator on the module. So yeah, first of all, when the capital W, when we are talking about the trivial module, namely the W equals to V, in this case, the D operator is defined using the recursion property, basically speaking. But the problem is actually, so if you want to use the philosophy that all the defining properties for an algebra should hold, then the problem is actually, so this of that definition does not automatically make sense in the context of a module.
I have a question, Shay. What's the
Yes.
grading condition on the modules? Is there any grading condition?
Yeah, you should have grading conditions. Yes, that's right. So the only
integer graded also?
It should be graded. It should be graded by C, and the only requirement is actually so when when the subscript is actually sufficiently negative. So the real part of the is sufficiently negative, then you should have the homogeneous space should be 0 over here. And these D bracket formula automatically holds because there should be a grading on them. There should be a grading on the modules. But on the other hand, whether or not there should be a capital D operator, so there has been a discussion very recently, actually, about the situation.
I understand. So you're saying the person that's like L0 will.
L0 always.
The discussion is about the derivative. Okay.
That's right. That's right. But the L-1, whether or not the L-1 should exist, so this is actually becoming a problem recently. So because in the earliest formulation of Masva by E.G. Huang, so he required the existence of DW operator on the left module W, and satisfying a similar similar relation over here. So you see that this identity really doesn't require anything about the DW operator. What's going to matter is really going to be the D-commutator formula. So Huang required this condition because he believed that, eventually when we are trying to consider the intertwining operators among the modules, so to allow the derivatives of the intertwining operators, we need to have a capital D operator. Okay, so I also follow the same belief until August when I was working out the fermionic construction of of Masva, and it's recently found that such an operator may not exist. There is actually a proof that there is on the special example of meromorphic open string vertex algebra and a Z2 twisted module. So I prove that it is impossible to find such an operator satisfying this property over here. So this is actually why the capital D operator is becoming a problem. And later it turns out that the capital D operator it seems that we shouldn't really assume it for the left modules. So for the rest of the talk, I will just use the terminology left V module without the capital D operators for the situation. So basically speaking now, generally speaking, a left module and a bi module should have a L-1 operator, but then into the most general sense, it's not necessarily guaranteed to exist. Okay, so this is actually something really new, actually. So none of the discussion were finalized until very recently. Okay, so now let me actually start with the co-definition of cohomologies. So recall that the Hochschild cohomology was defined over the home space of a tensor N to B, and also in the definition of the co-boundary operator, you need a left action, you need a right action, you need contractions, and all these operations are equipped with the variables. So in order to carry out the same computation, same formulation to vertex algebras, it is necessary for us to consider something. The cochain complexes we are supposed to have in this context should be equipped with the variables. So this is actually one of the technical points over here. So how to get these variables incorporated into the system. And this is actually Huang's important idea of using the so-called the space of W bar value, the rational functions. All right, so let me actually go over the definition. So let V be a vertex algebra, and then let W be a V by module. So then for a fixed number n, fixed positive integer n, we will consider f sub nc to be the so-called configuration space, namely the set of points in Cn such that the coordinates are all different. So this is traditionally called a configuration space in mathematical physics. Then a W bar value, the rational function in Z1 to Zn with the only possible poles at Zi equals to Zj. What a terrible name! But unfortunately, fortunately, this captures all the important information. So such a rational function is simply going to be a map whose domain is the configuration space, and whose image lies in the algebraic completion. So W bar is the direct product of Wn over here. So just notice that, so basically speaking, for a vertex operator y, v, z, w, if you evaluated z equals z as a complex number over here, then the grading properties allows you to say that such a guy sits in the algebraic completion. So this is one of the reasons why we really need L0 operators. Otherwise, none of these notions will actually make sense. So L0 is important. Okay, so its image has to lie in here, and then the only requirement is, well, if you pair this image with any guy in the restricted deal, then you are supposed to end up with a rational function in Z1 to Zn with the only possible poles at Zi equals to Zj, where I does not equals to j. So this is actually the first condition. The second condition is actually not that important. This condition is mainly used to handle the situation where the module is not gradient restricted. So namely, the homogeneous vectors for homogeneous subspaces are going to be like infinite dimensional. But we basically requires only a formal variable. We will only require a formal series such that the evaluating this formal variable into the complex numbers, and we are supposed to recover the same rational function. So this is actually not that important. So this is just like a technicality to allow modules with infinite dimensional homogeneous spaces. All right. So an immediate example of such kind of, let me actually give a very simple example. So suppose we consider the vertex this element. So let me say that y of v1 z1, y of v2 z2, and then over v over here. So if you do it over a generic element v over here, then you know that z1 equals to 0, z2 equals to 0, they are all supposed to be poles. However, if you require everything to be acted on the vacuum, then the map sending z1, z2 to such an element inside the algebraic completion. So this will form a v bar valued rational function with the only possible poles at z1 equals to z2. So in particular, z1 equals to 0 and z2 equals to 0. They are not supposed to be poles over here. You could actually extend this definition to arbitrary many variables. So for example, so if you set this guy part to be y of v1 z1, and you form the product all the way up to vn zn, and then you act on the vacuum over here, then this is another type. This is an example of v bar valued rational functions considered over here. All right, so this is just, so all these definitions just comes very naturally. And now, so we will just use the notation tilde, w tilde sub z1 to zn to denote the space of all such w bar valued rational functions. And now, in order to define the cochain complexes, we will define it over the space spanned by linear maps. So here, the descending v tends n to the space of w bar valued rational function. So this is basically analogous to the Hochschild situation where you have collinear maps to a bimodule over here. So this is actually how we place these variables into the theory. So the variables are in the theory using these w bar valued rational functions. Okay, so but of course we are not going to be using all such linear maps. We are going to use special classes of the linear maps. So the first class of conditions are the following. So first, it satisfies certain like D conjugation property and D derivative property. These properties, I don't think I want to explain them very in greater detail over here. But basically, I can tell you that the idea of these properties are basically means, well, we are only choosing the linear maps that behaves well with respect to the lower D and capital D operator. So L0 and L-1 should behave well. The linear map should behave well with the L0 and L-1 operators. So these conditions are motivated not just by the operator compatibility, but mostly I think it's just about its geometric considerations. So we know that the vertex operators can be understood as some structure over the punctured spheres. So similarly, the maps we are supposed to choose for the cochain complexes should admit a very similar geometry interpretation. So basically speaking, that's the idea. And in order to have those nice geometry properties, they have to behave well with the L0 and L-1 operators. All right, so this is the first set of conditions. I mean, these set of conditions, well, they look complicated, but it's not really that bad. What's really bad is actually the next condition, is composable with any number of vertex operators. And this condition is actually very complicated in the sense that even in Huang's earliest paper, he actually made a mistake about this. So his condition was actually, it turns out his assumption turns out to be insufficient, and he had to post a correction on the on the website. So okay, so this is how the condition looks like, and this is definitely looking very horrible. So, but the point is that this condition is very natural in the following remark. So first we have got a bunch of left action operators, and we have got a bunch of right action operators, and in the middle, so for the inputs of the phi map, we have got a bunch of contractions, basically the products of things over here. And we will require that, these kind of series has to converge. And so they have to converge in the appropriate region, and the sum can be analytically extended to a rational function, of the similar pole structure over here. And moreover, we require the poles to be bounded above by constants depending on the corresponding locations. This is actually, so basically speaking, this is what the condition says. But to understand it, all you need to, the following remark should help you to understand the situation. So in the context of associative algebra and a bimodule M, so you could actually, so given a linear map in the middle, you could actually contract all the way you want, and you can left action by any number operator, and you can act from the left and from the right by any number of elements in the algebra, and you should be able to contract all the way you want. In the context of associative algebras, all these operations make sense automatically. But then, because vertex algebras, generally speaking, so these operations, because operations are equipped with variables, and the operations make sense only when the variables are carefully chosen. So basically speaking, that's how we developed, that's how we figure out that this is actually going to be the necessary condition to make sure. So simply, we are to summarize in short, we are only looking for the linear maps where we can perform contractions, left actions, and right actions arbitrarily as we want. So that's basically the idea of these composable conditions over here. Okay, so with this setup over here, so basically speaking, that's called, so linear maps sending v tensor n to w2.z1 to zn, so these will be the linear maps we use to construct the cochain complex. And so once these conditions are figured out, then we can define the coboundary operator. So here, regarding coboundary operator, there's another important fact, and that's important that has to be mentioned, and this is precisely why we need to use W bar valued rational functions. So the coboundary map is basically defining a similar idea. So for the first term over here, we will just let we will just allow one vertex operator act from the left. And the last guy over here, we will just allow one vertex operator acts from the right. So this is actually like the right module action over here. And in the middle guys over here, we will just use the contractions to define the middle sum over here. So then the convergence condition we have assumed will be sufficient to make sure the convergence of each individual term over here. And then we just use the same idea from the Hochschild cohomology to define the coboundary operator. Okay, but now here is actually a very important part. So it is vital to use the W bar valued rational functions here, because the defining series for each term in the coboundary operator, so they do not have common regions of convergence. So if we scroll back to the previous page over here, and if you're familiar with the with vertex operator, so you can think of you can just use the case v equals to y of v1 z1 all the way down to y of vn zn acting on vacuum. You could just simply use this as as an example over here. So then if you act the vertex operator from the left, So then you see that this series actually converges when Z1 will be greater than all the rest. But then for this series to converge, Zn plus 1 will have to be greater than all the rest. So the region of convergence of these two series themselves, so these two series themselves, they do not converge. They have got empty disjoint. So that's why it's we shouldn't be using series to define the cohomology theory. We have to work over the W bar valued rational function, namely the analytic continuations, to avoid the trouble of the components having disjunct regions of convergence. So this is actually one of the key part in Huang's construction over here. Okay, so I think this is basically the technical part about the definition of the Hochschild-Huang cohomology. And then once everything is fixed out, then we could actually say that. So Huang proved that in the vertex algebra case, so the composition of two cobinary operators gives you 0. And I extended this result to meromorphic open-string vertex algebras into the non-commutative case. So this all holds. And then we have got a similar Cauchy complex, and then we define the nth cohomology group as the kernel of delta over image of delta as regularly. Okay, so regarding this part over here, so one of the most important examples is just the first cohomology group. So for the first cohomology group is can be described relatively easily. And actually, in this talk, we are only going to use the first cohomology. So let me just illustrate the definition. So we will call a gradient preserving. So here is actually the important word. So gradient preserving. We will call the gradient preserving linear map to be a derivation if, well, the obvious property is satisfied. So F applied to the product equals to left action on F and then plus right action on F. So that's basically the definition of derivation. So the key points to say is actually like a derivation because the gradient preserving. So because given a vertex gradient restricted, the algebra and vertex algebra and modules actually, so such kind of the choices of such gradient preserving maps are finite dimensional. So it's pretty easy for us to actually classify all such kind of derivations. Okay, so these are just the space of derivations. And moreover, a gradient preserving linear map is called the inner derivation if it's given by the action of the element. So f of v so there exists an element inside the zeroth Cauchy complex such that f of v equals to the left action of v on w subtracted by the right action of v on w. So it's basically like in the associative algebra case, this corresponds to the f of v equals to v times w minus w times v. So this is what we call the inner derivation in the associative algebra case. Then just similarly as an associative algebra, the first cohomologies are simply going to be isomorphic to the spaces of outer derivations, namely the quotient by the inner derivations over here. So that's
so I don't understand in the FV and that the module structure you have this 0 in the places of
yes, this is a very good question actually. So the reason for this is the following. If you really go deep into this this definition of zeros cohomology Cauchy complex, because I never got a chance to actually write it down very clearly. So basically speaking, so for such kind of Cauchy complexes, it's necessarily the dw x on w has to be equals to 0. So in other words, elements inside the zeros Cauchy complex is basically vacuum-like. Meaning that the left action and the right action of the vertex operator on the element inside the zeros Cauchy complex, they are all power series. And because they are all power series, we can evaluate at 0 over here. Yeah, this is actually like a technicality that I couldn't talk too much in detail over here. But basically speaking, so for these kind of elements, for these kind of vacuum-like elements, because the resulting actions, these two series, they are all power series without negative powers. So you could take the constant term. So that's basically what this inner derivation is defined. All right, so and I have to say that this is really a notion only for meromorphic open-string vertex algebras. In the context of vertex algebras, generally speaking, such kind of vacuum-like element only exists when w equals to v. So Yeah, I think that we don't see many such. So I think in the context of vertex algebra, so basically the zeroth quotient complex is normally going to be it. It's generally it should be 0 actually. So that's the general situation. Yeah, this is actually a good question. I couldn't, but unfortunately I couldn't explain more details. Okay, so yeah, let's continue because I think I'm running out of time. All right, so okay, so now regarding the first cohomologies in associative algebra, we have the following results. So first, an associative algebra is semi-simple if and only if all the first cohomology vanishes for all area A by module B. So naively, we would think, okay, maybe this should hold for vertex meromorphic open string vertex algebra as well. And unfortunately, this is not really the case. For a vertex algebra, it appears that the expected semi-simple criterion changes and becomes, okay, obvious a stupid typo over here. So it becomes H1 equals to Z1, where Z1 is the space of zero mode derivations. So zero mode derivation simply means if you have got an element in, so it's given by the residue. So if you're given by the residue of YWR of WXV, and then you take this residue at Z equals to X equals to 0. So this is basically like the zero mode of W on the V via the right actions over here. So yeah, so this is actually the difference between the vertex algebra and the comic and the associative algebra. So, but there is a philosophical explanation for this behavior. So philosophically, these extra derivations exist because a vertex algebra can also be interpreted as an analog of a Lie algebra. So the zero mode derivations we have obtained in this context are in many ways like the inner derivations of a semi-simple Lie algebra. So you might recall that the inner derivation of semi-simple Lie algebra, these are simply defined by the by the bracket operation. But these guys are generally outer derivations of the universal enveloping algebra. So they are not supposed to be inner derivations. Because our Hochschild cohomology is really a cohomology about the universal enveloping algebra, actually. So that's why it's not able to capture the zero modes of the Lie algebra. So this is actually. So I think this is actually like a philosophical but mathematically non-rigorous explanation. So, but I will be very glad to see a mathematically rigorous conceptual explanation for this behavior over here.
Fei, and this condition, this changed condition has been checked for which semi-simple vertex algebra?
For affine, Virasoro, and lattice, it has been checked. Yes, this was actually my paper on the letter of mathematical physics. Yeah. Yeah, it's actually very straightforward because I would say this is a very easy computation, but all you need to do is patience. So just classify all the derivations. But on the other hand, there are certainly, so the condition certainly not hold. There is I also have obtained examples where this condition doesn't hold. So, but in that case, the algebra is not semi-simple. So yeah, everything has been tracked. So for those three basic examples, I think things have been tracked. Okay. Okay, so now actually, let me actually discuss, come back to the extensions or in the cohomology over here. So because I'm left with like 15 minutes, so let me just go over the computation really quickly. So the main technicality is to develop a module, a meromorphic open string vertex algebra by module that is analogous to the space of linear maps. And this is actually what we should do. So now we start with W1 and W2 to be two left modules without the D operator. And let W2 hat zeta be the space of W2 bar valued rational functions with only one variable, but now I'm allowing zeta equals to 0 as a pole. So then this is actually, we use the different notation cap to simply means it's more than something in tilde over here. So we can recall that W2 zeta, if you use the tilde over here, so the old space of W2 bar valued rational functions will have no poles at zeta equals to 0. So basically speaking, what we get is kind of like a polynomial function. But now we are allowing poles in this case. So W2 hat is going to be a larger space than W2 tilde. Okay, so then we will let Hn to be the subspace of the linear maps sending W1 to this extended W2 value the rational functions. And then we will just denote the map by phi of zeta W1. And we require this space to be satisfying nice properties. I mean, the first property is still not that bad, but the next two properties are actually pretty technical. It requires a lot of convergence. It requires the convergence of certain kind of series. So we have got a deconjugation property and the composability, and also the so-called n-weight degree condition, basically speaking. So, but there exists the conceptual explanations towards these complicated conditions. So basically speaking, in the context of vertex and associative algebra and the left modules A modules M1 and M2. So what we want is the maps that making sense of any numbers of algebra elements acting from the left together with n number of elements acting on the domain over here. So we will allow any numbers of algebraic elements acting both on the codomain and the domain. So basically, we want to make sure that the convergence should hold. So this is actually the composability. This is basically what the composability condition is about. So we just need to make sure that such kind of series, left action on the codomain and action on the domain, we want to allow all such kind of series converge. So these are all natural conditions. The next condition is the n-weight degree condition, and this is also technical. It's about the expansion of the rational function they considered in the previous slide. So conceptually, this condition is necessary for the bimodule to have n as the lowest weight, so that the weights of the h in the bimodule is, so these weights are lower bounded. All right, so this is basically the idea of the constructing the bimodule. And then we will just define the left action and the right action by the following. So remember, in the associative algebra, so the left action was defined by the action on the domain. So here, what we would do is the same. So we will allow this is actually action on the codomain. So we will want to allow the action of a vertex operator on the codomain, so namely on the image over here. So this is the left action. For the right action, similar story. So we would like to allow f of am to be the action on the domain. And yeah, this is precisely the action on the domain over here. But there is a technicality about the expansions over here. So then, because now, so originally these series, they are supposed to be series with coefficients in W2. But now, because we are defining the action on H, so we need to actually obtain the analytic continuation as W2 bar value, the rational function. Then we need to expand them in the correct way so as to end up a series with coefficients in the bimodule. So this is actually a very technical part. And I think in the first version of my joint paper with Huang, it's actually, we probably took like 3 to 4 pages to explain how to understand these actions very correctly. Okay, so I think this is actually one of the difficult parts of this theory. But then once this part is overcome, then the grading operator and the capital D operators are defined naturally. Then we can actually check that now we do have the bimodule. So basically the verification of the bimodule condition basically occupies the majority part of my thesis, unfortunately. So, all right. So, so this is basically the theorem we have proved. We have obtained in my thesis, and now we could actually. So regarding the extension over here, so given a meromorphic open string vertex algebra and given 2 left modules without D operators, so we could define the extensions, their equivalence classes, similarly using the exact sequences. I mean, this is there does not exist any technicalities over here. However, to really characterize the general extensions, we will have to first focus on a special class of extensions satisfying some natural conditions. So this is actually the condition over here. So we will just use the XTN1 to denote the subset of equivalence classes of extensions such that there exists a section C for the map, so recall that the original exact sequence basically looks like this, and the P map is the projection, or from U to W1. And then we will require that this P map admits a section, but this section is not going to be a homomorphism in terms of vertex algebras. This is just like a linear map. We will just require a section of C linear maps, such that the extension is going to be given by such that the extension as a vector space is the coproduct of W2 and the image of the section. And moreover, we will require that these guy, so this pi2 over here, pi2 is basically another section of the inclusion, and this is actually my PCB over here. We will require the composition of pi2 and the vertex operator of U, and together with the section over here, we will actually require that these guys form an element inside each. And in other words, I should be able to add any numbers of vertex operators from the left, and also I should be able to add any numbers of vertex operators on the domain on the right. So this is actually the action on the codomain, and this is actually the action of the domain. So basically, that's the understanding. That's what this HN condition means. Okay, with this in mind, then I managed to prove that ext and W1, W2 is in one-to-one correspondence with the first cohomology, and I'm missing a hat over here. So there should be the first coaxial cohomology of V with the images in the bimodule over here. All right, so then necessarily you ask, is it very restrictive? So here are two observations. So first observation is that in the case of VRSO or VOA, and if W1 and W2 are special kind of freely generated Verma modules, then this condition holds for every extension in W1 and W2. So this is actually one. So that at the very least, actually, so in this case, EXTN1 is going to be equals to EXT1. So basically, the additional condition we demand on the extensions really is not really a big deal in this case. And Huang also figured out, I think the first observation was by Huang. Huang also figured out that if V contains a strongly rational C2 cofinite vertex operator algebra, subalgebra of safety type, then we could represent, the point is actually we could represent such maps. So this pi2 and C can be chosen as homomorphisms of the subalgebra. Then we could use the convergence of intertwining operators to argue that everything satisfies this condition over here. So this is actually another situation over here. Okay, so now I should say something about.
Sorry, a question. What does this N mean? The lowest weight of V?
I would say in this situation, N is actually, so in this case, N is the lowest weight of V. I think this, I think this part might have to be corrected because in the recent revision, I think I managed to show that this is actually going to be EXT2. So I can pick N equals to 2 in this case. So this has to be corrected actually in the recent revision actually. But basically, so generally speaking, I would say that N is going to be the lowest conformal weights appearing in the intertwining operators. So that you could use that to actually consider N over here. Yeah. What I should say is actually yes.
But if V is a VOA, then its lowest weight is 0. So I'm confused about that.
No. Yeah, that's right. That it shouldn't be the lowest weight of V. That's definitely.
Okay.
Definitely
no. Okay, gotcha.
Yeah.
Thanks.
Okay. Yeah. All right. So now I have some reason. So the recent observations are the following. So indeed, requiring the V to contain such an algebra is usually very overkill because in such cases. There's a much easier way for us to do the extension, namely the simple current extensions, actually. So this is actually this is actually going overkill. But actually, as long as the convergence condition we want automatically satisfied if W1 and W2 are some simple V0 modules. First, we have to take care of V0 modules. And moreover, as long as the products and iterates or intertwining operators of V0 modules, they all converge, then we could similarly choose these sections as homomorphisms of V0 modules, and then we could use the convergence of products and iterates to guarantee that the condition for any extensions of W1 and by W2. So obvious extensions are affine algebras and its Heisenberg subalgebra. So then in this case, if you talk about the weight modules over here, then we should expect to, so then for the weight modules, dxt1 are completely captured by the theory over here. And moreover, the most important thing is, yeah, we do not need a conformal embedding from V0 to V, and we also do not need any tensor category structure on V modules, actually. So this is actually so the conditions are very weak. So it's going to be much weaker than the requirements of the single current extension. All right, so here's a program I should propose for the computation of ext W1, W1, and W2. So generally speaking, so let V be a VOA and let V be a subalgebra satisfying all the previous properties. So since every extension is represented by something like this, where these guys are falling in the tiny operators, so we may do the reverse engineering. We may expect to conversely classify all such kind of extensions by studying all possible intertwining operators of this type, and then we need to make sure that, so we need to figure out all the possible intertwining operators such that these forms a derivation, and this derivation lands in the ext, in the hn w1, w2. So this amounts to be asking for all the intertwining operators satisfying these derivation identity. So Shashank and I have discussed some special cases over here, and we found that, yeah, this derivation equation I'm listing over here, this is actually very, very restrictive. So it's completely possible that when you try to regard W1, W2 as the modules for the subalgebra, well, they might, the reducible modules might have infinite multiplicities, but because of this condition is really restrictive, we really expect to have only finitely many choices of such intertwining operators. So this is actually like I feel like this is actually like a promising program to handle, for example, like the affine view, the ext of W1, W2 for weight modules of affine VOAs in the non-admissible levels. So that's actually the idea. So, but still, actually, so this is actually still, yeah, we still need to actually do more experiments on the situation over here. All right, so I think that's all I want to talk about today. Yeah, thank you very much for your attention. And if you have any questions, yeah, please feel free to ask.
Thank you, Fei. Thank you so much. We asked a lot of questions, but there may be some more. Let me stop the recording.
Sure.
Thank you, Fei.